Welcome to This Explainer. Today, we're diving into a masterclass on a topic that is absolutely crucial to how we interact with the built world around us. We're going to unpack disaster management, but specifically, we're looking at the engineer's role in building true, lasting resilience. When most of us hear the word disaster, we instantly picture the evening news, right? Rescue workers, government aid, these massive, uncontrollable acts of nature. But today, I really want to shift your perspective on that. We're going to look at this not just as passive observers, but through the rigorous analytical lens of sustainable engineering. So let's jump right in.
Okay, think about this for a second. When a massive earthquake strikes or a sudden flood completely paralyzes a city, we're so quick to blame the weather or the tectonic plates or whatever the event is. But let me ask you, who laid out that city that flooded so disastrously? Who designed the bridges that just couldn't handle the current? Who ultimately built the buildings that collapsed? The uncomfortable truth here is that disasters are rarely just natural events. Deep down, they are fundamentally failures in human design.
And that realization brings us to this brilliant quote from Dr. Arun, which is really the core thesis of our entire session today. As civil engineers, we're the first line of defense. We literally build the world. And because we build it, we have this profound choice in front of us. We can build our infrastructure to be fragile and vulnerable, or we can choose to engineer it to be resilient. Our goal today is to figure out exactly how we can build a world that doesn't just barely scrape by during a disaster, but actually bounces back stronger. So here's our roadmap for today's explainer. We'll quickly define what a disaster actually is, break down the core engineering challenges, walk through the four-part management cycle, look at how we design for the future, and then I'm going to leave you with a real-world challenge. All right, Section 1, Defining the Disaster. Let's get clear on the critical difference between a simple hazard and a true vulnerability.
Let's look at the precise academic definition for a moment. A disaster is an event, whether it's natural or man-made, where the needs of an affected community completely exceed its capacity to cope. Notice the specific phrasing there. A heavy rainstorm, well, that's just a natural hazard. But it only turns into a disaster when it hits a city that has completely inadequate drainage, completely overwhelming the community's capacity to cope. A disaster is literally the intersection of a hazard and a vulnerable population. So when you look at it that way, mitigating a disaster is, at its core, a design and engineering problem.
Now, we generally categorize these events by their speed and predictability. On one hand, we have sudden disasters, your earthquakes, landslides, flash floods, things that strike with little to no warning. On the flip side, we have slow onset disasters. These creep up gradually over time, like sea level rise or severe, prolonged droughts. To put that into perspective, if we look at a highly disaster-prone country like India, you have millions of people vulnerable to both of these categories. And as engineers, we can't just view that as an unfortunate statistic. That is millions of design flaws just waiting to be solved. Moving on to Section 2, the engineering challenge. Let's actively deconstruct exactly why catastrophic failures happen when natural forces meet human infrastructure. Understanding the actual mechanics of failure is crucial here. Let's map out 4 really common hazards. First up, earthquakes. Like we said, the earthquake itself doesn't kill people. A poorly built building does. The real engineering challenge here is ground shaking. Look at Japan. They experience massive earthquakes all the time, but their death tolls are remarkably low. Why? Because they engineer their structures with incredibly flexible materials like wood and use very specific foundation connections to actually absorb that shock. Second, flooding. This is the most widespread hazard. And why do we flood? Usually because we build right on top of floodplains or we fail to design drainage systems that can handle modern intense rainfall. Third, landslides. These usually happen when we completely ignore slope geometry or the chemical weathering effects of water. If you just cut into a hillside to build a road without understanding the soil mechanics, you aren't just building a road. You are essentially engineering a future landslide. And finally, cyclones. We obviously can't stop a massive storm, but we absolutely must calculate the extreme wind loads, that physical force pushing against the structure to prevent a total collapse. That brings us to Section 3, the disaster management cycle. Now that we understand those physical forces, let's look at how modern engineering is shifting away from just reacting and moving toward proactive anticipation. Historically, the engineer was just the person with a hard hat and a clipboard who showed up after the tragedy to help clean up the mess. But that purely reactive mindset, it's completely obsolete today. The modern engineer's greatest impact actually happens long before the event ever occurs. The disaster management cycle relies on 4 rigorous phases: mitigation, preparedness, response, and recovery. let's break down what an engineer actually does in each of these phases.
Phase 1 is mitigation. This is all about actively reducing risk before the hazard strikes. And honestly, it's our most critical phase. For earthquakes, we use brilliant techniques like base isolation. That literally means installing flexible pads between a building and its foundation to act as giant shock absorbers. For floods, the answer isn't always just building higher concrete walls. Sometimes it's about restoring natural wetlands to act as massive natural sponges, or building check dams. To mitigate landslides, we have to stabilize those slopes. We do that by draining internal water pressure or by constructing gabions, which are basically these big wire cages filled with stone, or using concrete retaining walls to physically hold the earth in place. Then we move into phase 2, which is preparedness. This is where we plan for the inevitable. We design early warning systems with really sophisticated rainfall gauges and river level monitoring. But perhaps the most fascinating concept here is something called anticipatory design. Let's look at Japan again. They brilliantly design everyday buildings like their public schools to serve dual purposes. During a crisis, they instantly become emergency evacuation centers. These schools are built with extra large balconies for quick access during floods, they have roof pools that store emergency drinking water, and they have independent solar panels to provide localized power when the main city grid goes down. That level of ingenuity is exactly what we need. They are literally baking the emergency plan right into the everyday design. Next up, phases 3 and 4, response and recovery. When the disaster actually strikes, Urban Search and Rescue, or USAR, engineers are deployed. These are highly trained specialists who assess the structural integrity of collapsed buildings to figure out the absolute safest angles to breach the concrete and reach survivors without causing a secondary collapse. They also conduct rapid post-event safety evaluations of the surrounding area. And finally, in recovery, the goal is never, ever just to return to normal. Normal is what failed in the first place. The modern engineering mandate is to build back safer. We have to take the painful lessons learned from those structural failures and apply new materials and much better designs so the new infrastructure is vastly superior. Section 4, designing for the future. We absolutely must adapt our engineering practices to face the escalating threats of climate change and rapid, dense urbanization. Look, the reality is that our world is changing, and fast. With a hotter atmosphere holding more moisture and huge populations densely packing into highly vulnerable coastal zones and floodplains, the frequency of extreme events is skyrocketing. But I don't want you to see this as a narrative of doom. It is actually an incredible opportunity for innovation. The United Nations Sendai Framework for Disaster Risk Reduction lays out a very clear global mandate. We have to protect our societal development gains by actively building resilience. We simply cannot allow a single storm to roll through and wipe out decades of hard-earned economic progress. And to achieve that kind of lasting resilience, the modern engineer has to blend different disciplines. In the past, we relied almost exclusively on what we call hard infrastructure, pouring more concrete, forging more steel, basically trying to fight nature head-on. But today, we have to integrate that with soft infrastructure. This means incorporating nature-based solutions, exactly like those wetland sponges we talked about earlier, right alongside our concrete retaining walls. It also means collaborating deeply with local communities and policymakers to create holistic environments that can actually adapt. All right, Section 5, the final challenge. It is time to take all of this theory and apply these principles directly to your own environment. Let's quickly review our core takeaways from today. Disasters are not just big storms. They are events that completely overwhelm a community's capacity to cope. They are almost always made worse or even entirely caused by human activity and poor structural design. Therefore, the civil engineer and really anyone involved in urban planning is our absolute first line of defense. Our greatest impact lies in proactive, anticipatory design. We need to create structures that expect, resist, and absorb the extreme forces of nature. So before we wrap up this explainer, I want to leave you with a final, provocative assignment, a real-world application of everything we've talked about. Tomorrow, I want you to step outside and take a really hard look at your own city, or even just your neighborhood. Find a spot that looks vulnerable. Maybe it's a brand new housing development built on a steep, poorly drained slope. Or maybe it's an intersection that floods every single time it rains. Or an old bridge that's showing major signs of structural stress. Identify it, document it, and then ask yourself, if you were the engineer in charge, how would you redesign it to be truly resilient? It is time we start looking at the built world not just for what it currently is, but for what it absolutely should be. Thanks so much for joining me today, and keep questioning the world around you.